Hello, everybody. And I'm sure we all are here to hear the answer to the question. What are the semantics of floating point in LLVM? And the answer is, I think, obvious to a lot of people. It's IEEE 754 with an asterisk. And why do we have the asterisk? There's a few exceptions. And honestly, it's when you get into the exceptions, that's when you're actually trying to answer with the question, what are LLVM's floating point semantics? So why is IEEE 754 not a complete answer to the question, what's our floating point semantics? For starters, not all types in LLVM, not all the floating point types are actually based on IEEE 754 types. The standard itself has a few moments of under-definition. For example, the behavior of NAND payloads or the definition of tininess. Hardware implementations frequently do things that are different from the standard. Sometimes these are additional features that they provide. For example, the option to do denormal flushing or providing extra operations. But sometimes you have to do deviations from the standard. For example, some embedded hardware might not have a floating point environment at all. The floating point environment is an instance of shared, hidden, mutable, global state, which as compiler writers, we all know is absolutely anathema for optimization. And finally, for many users, there are actually times where they would rather have the code be a little bit faster at the expense of a little bit of correctness, the basic premise of the fast math flag. So before discussing the floating point semantics as described by LLVM, let me start by going through a little bit of the hardware deviations that actually constrain our ability to give different semantics. One of the most notorious deviations, of course, is denormal flushing. And denormal flushing comes as two independent bits, really. You have the denormals are 0 bit, which says that if an input operand to a floating point operation is a denormal value, it should be treated as a signed 0 instead. And you also have the flush to 0 bit, which says that if the result of an operation is tiny, it should be flushed to a signed 0. And I do want to make a note here that there is a difference between saying that a tiny operation and a denormal operation. There are actually a few cases where you can have the result be a normal operand in floating point, and yet it will still get flushed to 0 when you turn on flush to 0. Some hardware allows you the ability to set denormal flushing on a prototype basis. You can, for example, choose to only do denormal flushing on 32 bits, while 64 bits does full support for denormals. And there's also some hardware that doesn't give you a choice. You have to do denormal flushing. For example, in x86, if you use AVX512 and bfloat16, that always flushes denormals independent of the denormal bits in the status register. One final annoyance is that some compilers, if you link using the fast math flag, that will set bits in the mode in the process startup that enables denormal flushing on an entire process-wide basis, independent of whether individual translation units were compiled with fast math. And this can cause problems. Another thing that is worth pointing out is the x87 FPU. This is mostly relevant for 32-bit x86 code, which means it has become less prevalent over the past few years, but it is a historical artifact that is still worth discussing because of its impact on floating point semantics. The central problem with the x87 FPU is that it only supports the 80-bit floating point type. If you want to load or store 32-bit and 64-bit floats, you can load and store those from memory, and that does an implicit conversion. And this is a conversion in the IEEE sense where the SNANs have to be quieted. And this can cause problems. For example, Rust ran into this, where if you have an ABI that returns a value on the x87 floating point stack, and it's a 32-bit floating point value, you cannot return an SNAN in that anymore. The other problem with the 80-bit type is that it's actually not large enough to sufficiently emulate a 64-bit floating point type without having double rounding, even if you try to do conversion immediately after every single operation. You can do it for 32-bit types, but not 64-bit types. Now, because the Java virtual machine people needed to have strict behavior for floating point, they did work out various methods you can use to do full emulation of double precision, which is a lot more complicated. It relies on a particular bit in the x87 FPU, which changes the precision control, and it means you have to do a lot of floating point environment stuff to do fully correct emulation of double arithmetic. And if you're familiar with LLVM support for x87, we do absolutely none of that right now. It's currently broken right now, and we know it's broken, but it has not been a high priority for anyone to fix because 32-bit x86 is not as relevant a platform anymore. And even when you do compile for 32-bit x86, we primarily default to using the SSE units, which don't have this problem anymore. The floating point environment is another major issue for hardware. Now, the IEEE 754 standard does mandate some level of support for the environment. In particular, it mandates the notion of dynamic rounding mode and also a little bit of exception support. Now, in floating point, exceptions are not the same as regular traps in hardware. You can actually both return a value and throw an exception at the same time. The default behavior.
I cannot understand your query, as it appears to be a series of disjointed phrases.
The default behavior for exception handling in floating point is to set sticky bits, which will always remain set until something turns them off, and someone actually looks at them. Now, some hardware also goes above and beyond and supports the ability to actually create hardware traps when an exception occurs. As mentioned earlier, a lot of hardware also has support for denormal handling bits. And there's also a variety of exotic bits and other architectures that change the value semantics in all sorts of weird, funky, and fun ways that makes it hard to design a general target independent floating point semantics for LLVM. And finally, I wanted to go over the basic operations of floating point. Now, IEEE 754 does define a basic set of core arithmetic operations. Your standard four-function arithmetic, comparisons, conversions, and also square root and FMA are considered core operations. And most hardware provides this full set of stuff. In addition to that, LLVM defines a set, IEEE 754 defines a set of additional arithmetic functions that map to standard elementary functions, primarily transcendental functions like the exponent function, trigonometric functions, A10, etc. These are much less common in hardware, and when you do see them in hardware, they tend to be at much lower precision than the other operations, which have to be correctly rounded. Now, finally, hardware can add other operations on top of that. You see a lot of that, especially when it comes to vector types. But another important case is you have low precision operations, because division and square root is implemented using a first inaccurate approximation with reciprocal and square root. That's a lot lower precision. And if you don't actually need the full precision, you can get a lot faster just by using the low precision version. Final trend I want to call out is that static rounding mode that ignores the dynamic rounding mode is starting to become increasingly prevalent in a lot of hardware, especially accelerator hardware, because it means you don't have to worry about the floating point environment anymore. And now that we have some grounding in what hardware and IEEE say about floating point semantics, let's start by looking at the semantics within LLVM IO itself. Now, there are some good parts of LLVM's floating point semantics. All of our floating point types have well-defined formats. The bit patterns of all of these are fairly well-defined. We also say that when you use these in integer operations, they all have particular expected behaviors. They're not going to change randomly on you. The NAND payloads won't change on you arbitrarily. I will also want to point out that as we've defined them, the fabs, fneg, and fcopy sign operations are effectively integer operations on the sign bit itself. So if you have weird funky NAND payloads, you can be guaranteed that LLVM won't change them on you if you pass them through these operations. Now, a few years ago, we did actually sit down and we actually worked out the full behavior for how we handle NAND payloads. It's effectively a kind of weak propagation. If you don't use weird NAND payloads, if your hardware doesn't introduce weird NAND payloads, LLVM won't either. But if any one of those situations is not true, it's anyone's game as to what happens. As part of that process, we also say that SNANDs are not required to be converted to quiet NANDs on operations. This lets us optimize 1.0 times x to a regular x expression. We can get rid of that fmul. And arguably the single most important rule we have for optimization is that in terms of the actual semantics of the value results of floating point operations, they have to be that is precisely guaranteed by IEEE 754. And the way you should read that is that an optimization cannot change that value. You cannot replace A divided by B with A times 1.0 over B. However, it is the case that we do have a lot of bugs in the back end and various codegen things. That means you don't necessarily get that same consistency if you actually rely on the back end doing stuff correctly. As Nikita mentioned in his keynote this morning, you have a lot more issues when you start going off the less common targets. And something else that we want to emphasize is the x87 behavior is considered to be a bug, even though because it lowers it without having to do any of the conversions to get exact 32 64-bit conversions. It's buggy, it's just not anyone's high priority to fix it. The floating point environment is where things start to get a little bit more weird. Now, LLVM sensibly assumes that the floating point environment is in the default state, that no one actually really cares about that for the most part. If you're familiar with C's rules for standard C FF access, this is effectively equivalent to saying FF access is off by default. And when we do this, we can assume that floating point operations are pure operations that have no side effects. And so they can be freely speculated, they can be freely added or removed as necessary. If you don't want those rules, if you actually want to play with the floating point environment, that's when you need to use the strict FP attribute. And once that's true, you can no longer speculate these operations anymore. However, as I'll get into the next slide, this does start to raise some questions about what the semantics of those operations are in that point. Another interesting wrinkle with the floating point environment is that the denormal flushing is not indicated using strict FP, it's indicated using denormal FP math, because it's used with fast math, not with I want to do more advanced environment stuff. And because of the problem with the front ends linking in the object file that turns us on for the entire process, this is not consistently correctly set by front ends that are working on a per translation unit basis. And it being a function attribute also shares some other problems, like it can't reflect the possibility that the environment changes in the middle of the function. Now, if you want to use floating point operations in a strict FP function, what you should do is you should replace them with constrained intrinsics. And these are intrinsics that are designed to have different semantics and designed to be environment aware. In fact, the original motivation for these was to be able to start by removing all of the optimizations we have for floating point operations, and only add them in when we know that they are safe to do so. Now, one thing you will note with the constrained intrinsics is that they are currently considered experimental, and these are not exactly new intrinsics. And so it's worth asking the question, has the experiment failed? I would actually argue, yes, the experiment has failed. We've noticed several problems with these intrinsics. The primary problem you have, of course, is there's a lot of duplication. This really became apparent when we added the vector predication intrinsics, because now you have to have 4 sets of intrinsics for every operation. One with constrained intrinsics, one with vector predication, one with both, and one with neither. And this becomes even worse when you have target-specific intrinsics, which don't have any of those variations in the first place. I don't think any of the backends have ever actually added a constrained version of any of their target-specific intrinsics. Now, if you want to do any optimizations on these, if, for example, you want to say, I want to use non-default rounding mode, but I don't care about any floating point exception stuff, and so you want to have optimizations that do assume non-default rounding modes, well, now you have to duplicate every single pattern in InScombine. And that becomes a problem in the compiler trying to do all of these patterns. It's just so much duplicated work that needs to be done. Some other problems that you may have noticed is the intrinsics don't actually specify, don't give you a way to specify more exotic floating point environment stuff. You can't add denormal stuff to a constrained intrinsic easily. And among the people who work on floating point in LLVM, there has been a tentative consensus that we do want to move from constrained intrinsics to using operand bundles. And we actually do have the sort of a patch to do this right now, but obviously it's not implemented yet. And so for the moment, your only option is to use constrained intrinsics. Now, the next thing I want to talk about is the problems of math library functions. And these are the functions that come from the IEEE 754 additional operations. And I'm not including square root or FMA as these kinds of libmem functions because these are core functions as far as most hardware is concerned. If you ask IEEE 754, all of these functions are actually supposed to be correctly rounded. If you ask the implementers of all of the math libraries, they say, that's too hard, we're not going to correctly round them. And as a result, that means all of the different libraries will give you different results for different inputs. Another problem you start to see with the math library functions is you can use them in two different ways in LLVM. You might use the C name of these functions with the C mangling, adding the suffix for the different floating point types, or you might use the LLVM intrinsic with the LLVM name mangling. And using the C for name mangling can be an issue because, for example, the long double type in C maps to 4 different LLVM IO types depending on what target you're compiling for. Another issue that's going to come up is the intrinsics are actually defined as equivalent to the LLVM function call, except it's not supposed to set any exceptions. It's not supposed to set error now. And this is a problem because if you look at how they work in CodeGen, they lower those calls to LLVM calls, which do set error now in most cases. Now we have some other issues with the math library functions. We are happily constant folding these intrinsics, which can change the results, especially if you're using a different library on your host versus the target you're compiling to, if it's an offload case or if you are cross-compiling for different architecture. Another interesting case that comes up is because this duplication between the C function names and the LLVM intrinsics, that the patterns that we actually have for optimizing various expressions will only match one or the other of them. There's actually surprisingly few cases where we match both of them. And the interaction of these functions with fast math flags can be interesting because when are we allowed to apply various mathematical identities? Do we need fast math flags to actually say that sine of minus x is equivalent to minus sine of x, the even-odd rules for functions? What about, is there some set of small constant values that we know we can constant fold that should be the same for all architectures, like sine of 0 should always be 0? But you also have the more complex expressions. When you have, say, sine over x over cosine of x, and you want to transform that to tangent of x because that's algebraically correct, what fast math flags do you need to do that? It actually turns out right now the answer is reassociation. How many of you expected that? Now, fast math flags, it turns out, is its own world of pain. Right now, it's currently specified primarily via these 7 flags which can specify in individual instructions. But it also turns out that we don't support fast math flags in all floating point instructions. In particular, we are missing them on the conversion instructions for no reason that I can find out. You can also specify these via function attributes, which are primarily only used by selection DAG during CodeGen, and we should be moving away from using those in all cases. The actual underlying semantics of these flags are, for the most part, extremely underdefined, and in many cases, it's not clear what they actually mean. If you've ever read the definition of AFN, for example. And I have been slowly going through all of these flags and trying to come up with better definitions for all of them, but it does take a lot of time to actually go through and analyze what should be the case. I can say with a lot of certainty, however, we do need a lot more flag bits. For example, reassociation does way too much. Not only is it used to say that you can do associativity and distributivity for floating point expressions so that you can, for example, do reduction trees, but it's also used for a lot of algebraic expressions like saying sine over cosine can be converted to tan, or other algebraic laws like that. Now, Andy is going to talk about this a little bit more in his next talk that's going to be in a couple of minutes, but there is also a problem that a lot of existing optimizations don't follow all the rules we already have for fast math flags. And in general, this is an area that needs a lot more work. Now, I'm sure you would love me to continue talking about all of the various problems we have with floating point semantics. It turns out there's not enough time in this talk to actually cover everything. But this is my various scorecard of about where we stand with floating point in LLVM. There are some features where we do well right now, for example, our value semantics, and there are some things that are completely absent, like we don't have any support for static value mode operations, and we basically have no support for low precision approximate operations. And there are things which are kind of half working, kind of half not working, like the floating point environment. And I will happily leave the slide up as people start coming up here to ask their own questions.
Thanks, Joshua. So if anyone has questions, ideally people can come up. There's a mic on a stand over here. There's not over here, so if there are questions on this side, I'll run the mic to you. Anybody? Yeah.
So one issue I've had consistently with the math intrinsics is that math functions will then turn into math intrinsics, which can then turn into math library calls. And that interacts really poorly with like LTO linking, because when you link your library via LTO, you don't actually have the symbols there. So the solution that exists upstream is that you just extract literally everything and then link it at a back-end level. So you'll just have every single math symbol in your application if you ever use those intrinsics for it. Do you have any input on that, or I think it's another issue?
I think in general we have a lot of problems with the math library stuff. I'm sort of hoping that as LLVM libc gets better and has more complete support for math library functions, we can switch to using that in a lot more cases and just solve a lot of the math library stuff simply by saying, let's just use the LLVM libc implementations for math library stuff.
So that would be like a back-end reduction, just immediately goes to that?
Something like that.
Okay, that'd be interesting. Thank you.
Thanks for the talk. So I'm curious about that point about the reusing possible implementations from LLVM libc. Is the idea like AP float appears to be missing all kinds of operations, potentially using LLVM libc in AP float specifically or something else? What are your thoughts on how that might look?
Well, I would love to use, so when AP float does the calls for libc, so when we do constant folding, for example, I would love to have AP float call into the LLVM libc for all of that stuff. It does not do that yet. I would also like to at least try to see if we could get some sort of code gen support for saying let's just link against libc as if it were like compiler RT or something for the libm functions, especially for targets that might not have a libm in the first place.
Because I really want the constant folding. We're leaving tons of performance on the table by not constant folding, like a bunch of these math calls with like immediate values at compile time. It's kind of sad.
It's one of those things where I think sometimes you want to do it, sometimes you don't want to do it. And it needs to be an option as to whether or not you do it. It can't be something we unconditionally do.
Okay, anybody else? Okay, well, thank you, Joshua.
Oh, sorry. I do have a related question. So do you happen to know the semantics in other toolchains related to the LV, like the semantic score like this? Like how GCC like FP semantics compare to the LVM, for example?
I'm not as familiar with the GCC's internal logic for stuff. My understanding is that its semantics are a lot more based on turning off optimizations entirely, rather than having an intermediate language with fully defined semantics. I'm just not familiar with it, I'm sorry.
Okay, for real. Thank you, Joshua.